Now that we've seen how to transfer loads from element to element across a structure, for example from the deck to a beam, to a girder, to a column and down to the foundation, doing that all without any numeric input at this time other than the lengths of the members, let's see how this works for transferring loads. Now, in order to understand this, we have to actually look at the construction because the loads are dependent on the construction. So let's imagine taking a cross-section somewhere through the structure, maybe over here, looking to the right. And we can envision the different constituent components of the structure. So, for example, we may have elements of decking. Perhaps this is wood deck. I know I said in the previous video that it was steel deck, but it really doesn't matter. We'll say wood deck to correspond with another tutorial I have elsewhere. So this is our structure. And that structure is comprised of the deck and the beam. And we'll give a weight on that of 5 pounds per square foot. On top of the structure we may have a floor finish. It could be tile, could be carpeting, could be any number of things. And we'll say that's 2 pounds per square foot. Below the beams, perhaps we have some mechanical systems, maybe some pipes. So we'll allow, for mechanical, we'll allow 2 pounds per square foot there too. And then all of that may be hidden below a ceiling. And we'll say that's 1 pound per square foot. These all values depend on the materials used. So that's 5, 6, 7, 8, 9, 10 pounds per square foot. And this is our dead load. We add on to that our live load. And we'll say this is 40 pounds per square foot, to give us a total of 50. So this is then our design load. So we'll apply that load to our structure here. So we have total load, $50 pounds per square foot. So that means if we were to look at our flooring planks and we divide this up into little squares, each of these individual squares, that's 12 inches by 12 inches, is equal to 50 pounds. So by virtue of our idea of tributary width, half of that load is getting carried by one side and half is being carried by the other side, just as a beam distributes, if the load is symmetric, it's distributing it equally to each side. So that's how our tributary widths come up. Again, so this is 5 feet. So for beam B1, we can see that the load on B1 our uniform load W is going to be equal to the load, the area load, times the tributary width. So that is our 50 pounds per square foot Notice I do not use PSF in my calculation because I can't cancel that with anything other than PSF. So I multiply that by my 5 feet. Now I cancel one of those, and I get 250 pounds per linear foot, since I dropped out one of those. So that is my uniform load, 250 pounds per linear foot. Or we will often write pounds per foot. Now, our beams labeled B2 also have a true width of 5 feet, and also G2 has a width of 5 feet. So for all of these, the W is the same 250 pounds per foot. So now we can compute the end reactions of these, because these end reactions then become loads either to the columns or to the girders. So let's do that calculation separately for clarity. So in the case of B1 and B2, since their lengths are both 10 feet and they have the same load, they have the same reactions. In fact, B1 and B2 in this instance are identical. They've just been labeled differently because of the direction change and just for clarity. So for B1 and B2, because this is totally symmetric, we can simply say that the left equals the right is WL over 2. In other words, half of the total load. So that is 250 pounds per foot times 10 feet over 2. We're going to cancel that, and we get 1,250 pounds per foot, pounds of reaction. Now for G2, because the length is different, it's going to be higher. So for G2, it's still symmetric. The reaction on the left and the reaction on the right are still WL over 2. But in this case, we have 250 pounds per foot and of length of 30 feet. So now we have 250 times 30 divided by 2, 3,750 pounds. So those loads go directly to the column over here, whereas the beam loads are going either to a girder or to a column. So next let's look at G1. Well, G1 is quite easy because it only has two concentrated loads that come from member B1. So this is a load here of 1,250 pounds. And since this is equal and symmetric, the end reactions are by inspection equal. So in this case we have 2 times P over 2. In other words, it comes out to P, 1,250 pounds. So that one's pretty simple. Now the one that gets more interesting is when we go to member B3, because G3 rather, because G3 has a single concentrated load from B2, whereas it has a uniform load along the right-hand side that comes from this portion of the deck over here. Since that's 5 feet, it's also going to be 250 pounds per foot, with a concentrated load of 1,250 pounds, because the end reaction for B2 on G3 is 1,250. Now in this case, because the beam is asymmetric, we no longer can simply say that it's half of the load. We must use our moment equilibrium to find the reactions. So I'm going to do the moments about the left-hand end equal to 0. And since the B2 reaction is in the middle, that leaves us 10 feet on either side of a 20-foot beam. So this becomes my moment center. I have 2 elements here that are rotating around, or with the potential, if this is the fixed point, load here, a load here, and then the balancing force is the right-hand reaction. So that says that I have 1,250 pounds with a moment arm of 10 feet. So that's B2, the concentrated load, 10 feet away. And if I call clockwise positive, that would go positive. Then I have my distributed load, 250 pounds per foot times 10 feet. This is my equivalent load that tends to act through the middle of this portion of the structure. Because it's a distributed load, take the total divided by 2, the balance point would be the middle. So then I need the moment arm, which is going to be 10 feet over 2. But be careful, because I'm measuring from the end here. So it's 10 feet over 2 to the center of this, plus another 10 feet. So actually the moment arm on this one is going to be 15 feet. I almost made that mistake. And then on the right-hand side, we have the reaction upwards at 20 feet, and that all balances to 0. So let's multiply all this out. So it's 12,500 pound-feet plus this is 2,500. Notice this is going to cancel, so it's pounds. 10 feet plus 10 over 2 is 15 feet. So my units are pound feet, so that's correct for moment, equals R right times 20 feet. So R right, I'm going to take that, expand this, 2,500 times 15. This is 37,500 pound-feet. plus 12,500 divided by 20. So that's 50,000 pound-feet divided by 20 feet. Gives us 2,500 pounds. Now, I could solve for the left-hand reaction by summing forces vertically, and the balance between the loads going down and those going up are the left-hand reaction. But as you can see, it's very easy to make a mistake here. So I'm going to sum moments about the right-hand side and then check using vertical equilibrium. If it comes out to 0, then I know I'm right. So this time I'm going to sum moments about the right-hand side equal to 0. So now distances are measured to the right-hand end. So I'm just going to take my P equivalent here, since I've already computed that. Now its moment arm is only to the center here from the end, so it's 5 feet. So again, this is the equivalent P. If I'm calling clockwise positive relative to this point, now my force is rotating counterclockwise, so this has to be negative, minus my middle load, B2, 1,250 pounds. That's 10 feet away. Now my left-hand reaction would rotate clockwise, and so that is a positive sign, and it's 20 feet away. So then, and this all balances to 0. That is left-hand reaction. So that's 2,500 times 5, 12,500 pound-feet. Plus another 12,500. So you see the feet are going to cancel here, and the answer will be in pounds, which is what we want. So that's 2,500 pounds, 25,000 pounds divided by 20. And that's our left-hand reaction. Now, to confirm this, let's check this using vertical equilibrium. So sum of the forces vertically equal to 0. Let's start with the loads. 1,250 pounds minus, and it's downward minus, and then minus 2,500 pounds. This again is the equivalent P. Plus our left, plus our right. Does that equal 0? Well, we can see right off that it's going to, because negative 3,750 plus 2,500 plus 1,200, negative 3,750 plus 3,750, that's 1,250 rather. That checks. So that is our final solution. And that is how we transfer loads through a structure from element to element and develop framing diagrams that we can then analyze using linear and rotational equilibrium to find the end reactions. And this is the very first step that we need to follow whenever we do an engineering analysis of a floor structure.